Tonight, we are going to think carefully about distance. Not the kind of distance that separates cities or continents, or even the distance between the Earth and the Moon. We are going to think about the distance between stars, the vast, cold, almost incomprehensible emptiness that lies between our solar system and the nearest point of light in the sky. And we are going to ask, quietly and without urgency, what it would actually take to cross it. Welcome to Sleepytime Universe, where the biggest questions in science are explored at the pace of a calm and restful night. The answer, as we will discover together, is not simply that the journey would be long. It is that the journey would demand things that physics itself may not permit, not technology we have not built yet, not funding we have not found yet. Physics, the laws that govern how matter and energy behave, laws that do not bend for ambition or imagination, and that apply equally to every civilization that has ever looked up at the stars and wondered whether it might one day reach them. This is not a discouraging thought. It is, in its own way, a profound one. To understand why the stars are so difficult to reach is to understand something deep about the universe itself, the nature of space, the behavior of energy, the limits of the human body, and the strange geometry of time at high velocity. Each of these barriers, considered slowly and carefully, reveals something worth knowing, and that is exactly what we are going to do tonight. We will begin where any honest account of interstellar travel must begin, with the distance itself, with the nearest star, and what it would mean to try to reach it. Chapter 1. The nearest star. The closest star to our Sun is a small, dim red dwarf called Proxima Centauri. It sits at the edge of a triple star system known as Alpha Centauri, a system that has long captured the imagination of astronomers and dreamers alike, partly because of its relative proximity, and partly because of the faint possibility that it might harbour worlds of its own. Proxima Centauri is, by the standards of the galaxy, practically next door, and yet the numbers involved in reaching it are staggering in a way that is difficult to absorb on first encounter. The distance to Proxima Centauri is approximately 4.2 light-years. A light-year is the distance that light travels in a single year, moving at just under 300,000 kilometers per second. In 1 second, light crosses a distance roughly equal to 7.5 times the circumference of the Earth. In 1 minute, it travels nearly 18 million kilometers. In 1 year, it covers approximately 9.5 trillion kilometers, and Proxima Centauri is 4.2 of those years away. To put that in terms that feel a little more grounded, consider the fastest spacecraft humanity has ever launched. The New Horizons probe, which was sent toward Pluto and the outer solar system in 2006, left Earth at a speed of approximately 58,000 kilometers per hour. It was, at the time of its launch, the fastest human-made object ever to leave our planet. At that speed, it reached the Moon in about 9 hours. It passed Mars in 47 days. It reached Pluto after 9.5 years of travel. At that same speed, the journey to Proxima Centauri would take approximately 78,000 years. That number deserves a moment of quiet. 78,000 years ago, modern humans were living in small groups across Africa, Europe, and parts of Asia. The last ice age was still thousands of years in the future. The oldest known cave paintings had not yet been made. Agriculture would not be invented for another 60,000 years. The entirety of recorded human history, from the earliest writing systems to the present day, spans only about 5,000 years. And yet, a spacecraft moving at the fastest speed we have ever achieved would need more than 15 times that span of recorded history just to reach the nearest star. This is the first and most fundamental problem with interstellar travel. It is not a problem of motivation or of engineering sophistication. It is a problem of distance so extreme that our intuitions about travel, about time, about what is achievable in a human lifetime, or even across generations, simply break down. The numbers do not fit inside ordinary experience. They require a different kind of thinking. To reach Proxima Centauri in a more manageable time frame, a spacecraft would need to travel at a significant fraction of the speed of light. If a craft could reach 10% of the speed of light, which is approximately 30,000 kilometers per second, the journey would take about 42 years. At 20% of light speed, it would take around 21 years. At 50% of light speed, roughly 8.5 years. These are timescales that begin to feel, if not comfortable, at least conceivable. A human being could, in principle, survive such a journey, but achieving even a small fraction of the speed of light is an entirely different order of problem from anything humanity has ever attempted, and the barriers involved are not merely technical. They are written into the structure of the universe itself. It is also worth pausing on what Proxima Centauri actually is, because it serves as a reminder that the nearest star is not a particularly inviting destination. It is a red dwarf, significantly smaller and cooler than our Sun, prone to powerful stellar flares that periodically blast its surroundings with intense radiation. In 2016, astronomers confirmed the existence of a planet orbiting within Proxima Centauri's habitable zone, a world now known as Proxima b. Whether that planet could support life is deeply uncertain. Its proximity to such an active star means it is likely subjected to radiation levels that would be hostile to life as we know it, and it almost certainly does not have the kind of stable, sheltered environment that Earth provides. But the point is not whether Proxima Centauri is worth visiting. The point is that even this nearest of neighbors, sitting just 4 light years away, is separated from us by a gulf so vast that it defeats every form of propulsion we currently possess. Beyond Proxima Centauri, the distances grow even more humbling. The next nearest star systems, Barnard Star, Wolf 359, Leyland 21185, are between 5.9 and 8.3 light-years away. The bright star Sirius, one of the most prominent objects in the night sky, is 8.6 light-years distant. Vega, another familiar point of light, sits 25 light-years away. The center of the Milky Way is approximately 26,000 light-years from Earth, and the Andromeda Galaxy, our nearest large galactic neighbor, lies 2.5 million light-years away. The stars we see on a clear night are not close. They are not even in the same category of distance as anything else we have ever navigated. The ocean voyages that connected continents, the flights that now cross them in hours, even the Apollo missions that carried humans 250,000 miles to the moon. These are, in the context of interstellar space, vanishingly small movements. They do not prepare us, intuitively or technologically, for what crossing even the nearest star system would actually require. There is something worth sitting with in that realization. We live on a world that orbits a star. That star is one of somewhere between 200 billion and 400 billion stars in the Milky Way alone. And between almost every one of those stars lies a silence so deep, a vacuum so extended, a distance so extreme, that the fastest things we have ever built would spend longer crossing it than human civilization has existed. The universe is not empty in the way that space between cities is empty. It is empty in a way that has no human equivalent, no scale we were built to understand. That is where we begin, with 4.2 light years, and with the quiet, careful recognition that the problem of reaching the nearest star is not a small one. Chapter 2. The Energy Problem. Once the distance is understood, the next question follows naturally. If we wanted to cross that distance in a reasonable time, say within a human lifetime, how much energy would that actually require? This is where the problem of interstellar travel moves from the abstract to the physical. Distance is a fact of geography. Energy is a fact of physics. And the energy required to accelerate even a modest spacecraft to a meaningful fraction of the speed of light is so large that it reframes the entire conversation. To understand the scale of the energy problem, it helps to start with something familiar. When a rocket launches from Earth, it burns through an enormous quantity of fuel in the first few minutes of flight. The Saturn V rocket, which carried the Apollo missions to the Moon, weighed approximately 2.8 million kilograms at launch. Of that total mass, about 2.1 million kilograms was propellant, fuel and oxidizer that would be consumed during the first stages of ascent. The actual payload delivered to the Moon was a small fraction of that total. This ratio, the overwhelming dominance of fuel mass over useful payload mass, is one of the defining realities of spaceflight, and it becomes catastrophically worse as the desired velocity increases. The relationship between velocity, mass, and energy is not linear. It does not scale gently. To double the speed of a spacecraft, you do not simply need twice the energy. Because of the way kinetic energy behaves, doubling the speed requires 4 times the energy. Tripling the speed requires 9 times the energy. As velocities approach a significant fraction of the speed of light, the energy requirements grow so steeply that they quickly exceed anything that can be produced by chemical or even nuclear means using any reasonable quantity of fuel. Consider a spacecraft with a mass of 1,000 kilograms, roughly the mass of a small car, and far lighter than any crewed vessel would need to be. To accelerate that spacecraft to just 1% of the speed of light, which is about 3,000 kilometers per second, would require approximately 4.5 times 10 to the power of 17 joules of energy. That is 450,000 trillion joules. For comparison, the total energy consumption of every human being on Earth across an entire year is approximately 5.5 times 10 to the power of 20 joules. Accelerating our small spacecraft to 1% of light speed would require roughly 1% of all the energy humanity uses in a year, delivered entirely to a single object weighing no more than a family car. At 1% of light speed, the journey to Proxima Centauri would still take 420 years. To reach 10% of light speed, the energy required increases by a factor of 100. To reach 20%, by a factor of 400. And this is before accounting for the fact that a spacecraft must not only accelerate to its cruising speed, but also decelerate at the other end. Otherwise, it would pass through the destination star system in a matter of hours, unable to stop, unable to study anything, unable to do anything useful at all. A mission that requires both acceleration and deceleration needs roughly twice the energy, and the fuel required to carry that energy must itself be accelerated, which requires more fuel, which must itself be accelerated, in a cascading relationship that rapidly becomes unworkable. This cascading relationship has a name in rocketry. It is described by what is known as the Tsiolkovsky rocket equation, formulated by the Russian mathematician Konstantin Tsiolkovsky in 1897. The equation describes the relationship between the change in velocity a rocket can achieve, the speed at which its exhaust is expelled, and the ratio of its initial mass to its final mass. What the equation reveals with mathematical precision is that as the desired velocity increases, the ratio of fuel mass to payload mass grows exponentially. For chemical rockets, which expel exhaust at speeds of a few kilometers per second, the fuel requirements for interstellar velocities are not merely impractical. They exceed the mass of known objects in the solar system by many orders of magnitude. Even with far more efficient propulsion systems, the energy problem does not disappear. It simply becomes less immediately catastrophic, while remaining deeply formidable. Nuclear fission rockets, which have been studied seriously since the 1950s, would offer exhaust velocities roughly 10 times greater than chemical rockets. Nuclear fusion, if it could be harnessed for propulsion, would do better still. But even fusion propulsion, which remains well beyond current technology, would struggle to reach the velocities needed for a journey of any reasonable duration. The energy stored in matter itself, through the complete conversion of mass to energy via processes like matter-antimatter annihilation, represents the theoretical upper limit of what physics permits. And even at that limit, the fuel masses required for crewed interstellar travel remain enormous. Matter-antimatter propulsion is worth considering for a moment, not because it is achievable, but because it represents the most optimistic case physics allows. When matter and antimatter meet, they annihilate each other completely, converting their entire combined mass into energy with perfect efficiency. No chemical reaction, no nuclear reaction, comes close to this energy density. A single kilogram of matter annihilating with a single kilogram of antimatter would release approximately 1.8 times 10 to the power of 17 joules, roughly equivalent to the energy released by a large nuclear weapon from just 2 kilograms of fuel. For an interstellar mission, this kind of energy density is the closest thing to workable that physics offers. And yet, even antimatter propulsion faces severe practical limits. Antimatter does not exist in useful quantities anywhere in the natural world accessible to us. It must be manufactured, particle by particle, in facilities like the Large Hadron Collider at CERN, at a production rate so slow and an energy cost so vast that producing even a single gram of antimatter would require more energy than humanity currently generates in thousands of years, and would cost, by some estimates, tens of trillions of dollars per gram. A crewed interstellar mission might require hundreds or thousands of kilograms of antimatter as fuel. The gap between what we can produce and what would be needed is not a gap that better technology alone can close. It is a gap rooted in the physics of how antimatter is made and how energy converts to mass. There is also the question of what the energy problem means for the size of the spacecraft itself. Any crewed mission to another star would need to carry not just propulsion systems, but life support, food production or storage, medical facilities, communications equipment, radiation shielding, and all the redundancy that a journey of decades or centuries would demand. These requirements push the mass of the vessel upward, and every increase in mass demands a corresponding increase in fuel, which increases the mass further, which demands more fuel. The engineers who have studied these problems carefully tend to arrive at the same conclusion. A crewed interstellar spacecraft, even one using the most efficient propulsion physics can plausibly permit, would need to be extraordinarily massive, and the energy to move it would be extraordinary in proportion. None of this means the problem is impossible to think about. Physicists and engineers have spent decades exploring concepts that attempt to work around the energy wall rather than through it. Laser-driven light sails, in which a spacecraft carries no fuel at all, but is instead pushed by a powerful beam of light directed from the departure system, represent one of the more credible approaches for very small probes. The Breakthrough Starshot initiative, announced in 2016, proposed accelerating gram-scale spacecraft to 20% of light speed using an array of ground-based lasers. At that scale, the energy requirements become more manageable, and the absence of onboard fuel removes the cascading mass problem entirely. But a gram-scale probe carries no crew, no life support, and no ability to decelerate at the destination. It would pass through the Alpha Centauri system in a matter of hours, transmitting data across 4 light years with a signal too faint to carry much information, before disappearing into the dark on the far side. The energy problem, in the end, does not merely make interstellar travel difficult, it makes crude interstellar travel, using any propulsion system grounded in known physics, something that requires either energy sources we cannot produce or fuel masses we cannot carry. Every serious analysis of the problem arrives at this same ledge. The numbers work only at the extreme edge of what physics permits, and even there, the margin is thin and the assumptions generous. This is not a temporary state of affairs waiting to be resolved by the next generation of engineers. It is a reflection of the universe's own arithmetic, of the relationship between mass, velocity, and energy that governs all motion at every scale. The stars are far away, and moving things across vast distances at high speeds costs energy in quantities that strain or exceed anything available to us. That is the second wall interstellar travel runs into, and it is built from the same physics that holds every atom in the universe together. Chapter 3. The Fuel Wall. The energy problem and the fuel problem are related, but they are not the same thing. The energy problem asks how much energy is needed to reach interstellar velocities. The fuel problem asks where that energy is stored, how it is carried, and what happens to the spacecraft as a result. And the fuel problem has a particular cruelty to it, because the harder you try to solve it, the worse it becomes. The core of the fuel problem is this: a rocket moves by expelling mass in one direction and using the reaction to push itself in the other. This is Newton's third law, applied to propulsion. Every kilogram of exhaust pushed backward accelerates the rocket forward by a corresponding amount, adjusted for the ratio of exhaust speed to rocket mass. The faster the exhaust moves, the more efficient the rocket. But regardless of how efficient the exhaust is, the rocket must carry its fuel with it. And fuel has mass, and mass must be accelerated. And accelerating mass requires more fuel. The equation folds back on itself in a way that becomes geometrically punishing at high velocities. This relationship was described precisely by Konstantin Tsiolkovsky, whose rocket equation remains one of the most important and most sobering results in all of astronautical engineering. The equation states that the ratio of a rocket's initial mass to its final mass, after all fuel is burned, grows exponentially with the ratio of desired velocity change to exhaust velocity. For a chemical rocket with an exhaust velocity of around 4.5 kilometers per second, achieving a velocity change of even 45 kilometers per second requires a mass ratio of approximately 22,000 to 1. That means for every kilogram of useful payload delivered at the destination, the rocket must begin its journey carrying 22,000 kilograms of fuel and structure. For the velocities required in interstellar travel, the mass ratios produced by the Tsiolkovsky equation become not just impractical, but mathematically absurd. To reach 1% of the speed of light using a chemical rocket, the required mass ratio exceeds 10 to the power of 280. That number has no physical meaning in our universe. There are estimated to be only around 10 to the power of 80 atoms in the entire observable universe. A mass ratio of 10 to the power of 280 is not a large engineering challenge. It is a demonstration that chemical propulsion is not a starting point for interstellar travel in any meaningful sense. It is simply the wrong tool for the problem, by so many orders of magnitude that the comparison becomes almost philosophical. Nuclear propulsion improves matters considerably. A nuclear thermal rocket, which heats a propellant by passing it through a reactor, can achieve exhaust velocities of around 8 to 9 kilometers per second, roughly twice that of the best chemical engines. Nuclear pulse propulsion, a concept studied seriously in the late 1950s and early 1960s under the name Project Orion, proposed propelling a spacecraft by detonating a series of nuclear bombs behind a large pusher plate. The exhaust velocities achievable with this approach could reach tens of kilometers per second, and the concept was studied with genuine scientific rigor. Calculations suggested that a large Orion-type vehicle could reach velocities of perhaps 0.1% of the speed of light, still far short of what interstellar travel requires, but orders of magnitude beyond chemical propulsion. Nuclear fusion propulsion represents the next step up the energy ladder, and it is the approach that serious studies of interstellar propulsion have most often focused on. Fusion releases energy by combining light atomic nuclei, typically isotopes of hydrogen, into heavier nuclei, releasing a fraction of their mass as energy in the process. The energy density of fusion fuel is millions of times greater than that of chemical fuel, and the exhaust velocities achievable with a fusion drive could in principle reach several percent of the speed of light. A study conducted in the 1970s by the British Interplanetary Society, known as Project Daedalus, proposed a fusion-powered interstellar probe that could reach Barnard's star, approximately 6 light-years away, in about 50 years. The spacecraft design required approximately 50,000 tons of fuel, the vast majority of which was helium-3, an isotope that is extremely rare on Earth, but might be extractable from the atmospheres of the outer planets. Project Daedalus was a serious engineering study, and its conclusions were sobering even under optimistic assumptions. The spacecraft it described was enormous, its fuel requirements were staggering, and the helium-3 needed to power it did not exist in accessible quantities anywhere in the inner solar system. A follow-up study, Project Icarus, revisited the Daedalus concept in the early 2010s and arrived at similarly challenging conclusions. Fusion propulsion might, in principle, make interstellar probes conceivable over very long timescales with very large investments. But the technology to achieve controlled fusion for power generation, let alone for propulsion, remains beyond our current capabilities. Decades of research into fusion energy have yielded genuine progress, but a working fusion reactor that produces more energy than it consumes has only recently become achievable under laboratory conditions, and the path from laboratory fusion to a fusion drive capable of propelling a spacecraft to interstellar velocities remains extraordinarily long. The antimatter option, as discussed in the previous chapter, offers the highest theoretical energy density of any known fuel. But the production problem makes it effectively inaccessible at the scales required. Even setting aside the cost and energy of production, antimatter is extraordinarily difficult to store. It cannot touch ordinary matter without annihilating, which means it must be held in magnetic or electric field traps, isolated from all physical contact with the storage vessel. These traps require continuous power to maintain. Any failure of the containment system results in the immediate annihilation of whatever antimatter remains. releasing an explosion proportional to the quantity stored. For a spacecraft carrying tons of antimatter, a containment failure would be catastrophic beyond description. Managing antimatter storage safely over a journey of decades or centuries, through radiation, through mechanical stress, through the inevitable degradation of components over time, represents an engineering challenge for which no credible solution currently exists. There is a concept that attempts to sidestep the fuel problem entirely, at least in part. The Bussard ramjet, proposed by physicist Robert Bussard in 1960, imagined a spacecraft equipped with a vast electromagnetic scoop, thousands of kilometers in diameter, that would collect hydrogen from the interstellar medium as it traveled and use it as fuel for a fusion drive. Since the fuel would be gathered from the environment rather than carried from the start, the mass ratio problem would be dramatically reduced. The spacecraft would accelerate continuously, gathering more fuel the faster it went, potentially reaching a significant fraction of light speed over a long enough journey. The Bussard ramjet captured the imagination of science fiction writers and physicists alike for decades. But detailed analysis revealed serious problems. The density of hydrogen in the interstellar medium is extremely low, roughly 1 atom per cubic centimeter in typical regions of space. Collecting enough hydrogen to fuel a fusion drive would require a scoop of truly vast dimensions, and the electromagnetic fields needed to operate it would themselves require enormous power. More fundamentally, later analysis suggested that the drag created by the scoop interacting with the interstellar medium would likely exceed the thrust produced by burning the collected hydrogen, meaning the ramjet would slow down rather than accelerate. The concept has not been entirely abandoned, but it has been significantly constrained by the physics of what the interstellar medium actually contains and how it actually behaves. What the fuel wall ultimately demonstrates is that the challenge of interstellar propulsion is not simply a matter of finding a better fuel or a more efficient engine. It is a challenge rooted in the fundamental relationship between energy, mass, and velocity. Every approach that carries its fuel faces the exponential cruelty of the rocket equation. Every approach that gathers fuel from the environment faces the thinness of interstellar space and the drag it imposes. Every approach that uses an external energy source, like a laser sail, solves the mass ratio problem, but introduces its own severe limitations around deceleration, crew survival, and the infrastructure required at the departure end. The fuel wall is not a single obstacle. It is a family of related constraints, each one a consequence of the same underlying physics, each one encountered from a different direction as different solutions are attempted. Moving through interstellar space requires energy on a scale that strains the limits of what matter can store and what engineering can manage. That is the third wall, and it stands behind the energy problem like a shadow, ensuring that even a perfect understanding of the energy required does not, by itself, bring the destination any closer. Chapter 4. Time and the human body. Even if the energy and fuel problems could somehow be resolved, even if a spacecraft could be accelerated to a meaningful fraction of the speed of light by some means not yet available to us, the journey would still have to be survived. And surviving an interstellar journey is not simply a matter of packing enough food and water. It is a matter of keeping human beings alive, healthy, and functional across timescales that have no precedent in the history of human travel, inside an environment that is hostile to biology in ways that do not apply anywhere on Earth, or even in low Earth orbit. The first and most immediate challenge is time. At 10% of the speed of light, The journey to Proxima Centauri takes approximately 42 years. At 20%, around 21 years. These are the more optimistic scenarios, the ones that require propulsion systems far beyond anything we currently possess. Even in the best case, an interstellar crew would spend decades in transit. They would leave Earth as young adults and arrive, if they arrived at all, in late middle age or old age. The world they left would have changed beyond recognition by the time any return signal reached home, let alone by the time they could return themselves. The psychological weight of that separation, from family, from culture, from everything familiar, is not a minor consideration. It is a fundamental aspect of the human experience of such a journey, and it has no parallel in any form of travel humans have ever undertaken. The human body was not designed for long-duration spaceflight. It was shaped by millions of years of evolution on the surface of a planet with strong gravity, abundant oxygen, a stable day-night cycle, and constant physical and social stimulation. Remove those conditions, and the body begins to change in ways that are well documented from decades of research aboard space stations. Bone density decreases as the skeleton no longer bears weight in the usual way. Muscle mass declines without the constant resistance of gravity. The cardiovascular system adapts to a fluid distribution that differs from the terrestrial norm, with consequences for heart function and blood pressure regulation. Vision can be affected by changes in intracranial pressure that occur in microgravity environments. The immune system behaves differently in space, in ways that are not yet fully understood. Sleep is disrupted by the absence of natural light cycles. The list of physiological changes associated with long-duration microgravity exposure is extensive, and while many of these changes are manageable over months, their cumulative effects over years or decades are far less certain. One partial solution to the gravity problem is rotation. A spacecraft that spins along its central axis generates centrifugal force that mimics the effect of gravity for its occupants. The faster the spin and the larger the radius of the rotating section, the closer the simulated gravity comes to the 1G environment humans evolved in. This is a well-understood concept, and it has been studied seriously as a component of long-duration spacecraft design. But it introduces its own engineering complexities. A rotating habitat large enough to provide comfortable simulated gravity at a rotation rate slow enough to avoid disorienting Coriolis effects would need to be substantial in size, which adds mass, which returns us to the fuel and energy problems discussed earlier. Artificial gravity through rotation is theoretically achievable, but it is not a trivial addition to a spacecraft design. Nutrition over a multi-decade journey presents its own challenges. Carrying food for 40 years is not practical, not in terms of mass, volume, or the stability of nutrients over such timescales. Any serious long-duration mission would need to produce at least some of its food aboard the spacecraft, using controlled agriculture systems that can grow crops reliably in an artificial environment, under artificial light, with recycled water and nutrients. These systems exist in prototype form, and research into closed-loop life support has been ongoing since the early days of the space program. But a fully closed agricultural system capable of supporting a crew for decades with sufficient redundancy to survive equipment failures and crop failures has never been built or tested at the scale an interstellar mission would require. The sheer biological complexity of such a system, the interactions between plants, microorganisms, atmospheric composition, and human metabolism is substantial, and the margin for error on an interstellar voyage, where resupply is not possible, is essentially zero. Water and atmosphere can in principle be recycled with high efficiency. Current space station technology already achieves impressive recovery rates for water from humidity, urine, and other sources, and atmospheric systems can scrub carbon dioxide and replenish oxygen reliably over long periods. But recycling systems degrade, components wear out, filters need replacement, membranes fail. On a journey measured in decades, the maintenance demands of life support systems would be constant and unforgiving. Every component that could fail would, at some point, need to be repaired or replaced, using materials and spare parts carried aboard from the start, since manufacturing replacements en route would require capabilities far beyond what current technology permits. The logistics of maintaining a closed life support system for decades with no external supply chain represents an engineering problem of enormous complexity. Beyond the physical challenges, the psychological dimension of an interstellar journey is profound and not easily dismissed. Human beings are social animals. We require not just the company of others, but meaningful relationships, purpose, variety, and connection to something larger than ourselves. A crew confined to a spacecraft for decades, isolated from the rest of humanity by distances that make real-time communication impossible, would face psychological pressures that have no equivalent in any environment humans have previously inhabited. Research on isolated and confined environments, Antarctic winter overstations, submarine deployments, long-duration space station missions provide some insight into how humans cope with isolation and confinement, but none of these situations approaches the duration or the absolute separation of an interstellar voyage. The crew of an interstellar mission would be, in a very real sense, the most isolated human beings in history, separated from their homeworld by distances that light itself takes years to cross. Crew selection and psychological preparation would be critical, but preparation has limits. The stress of confinement, the grief of permanent separation from everyone left behind, the anxiety of operating in an environment where any serious malfunction could be fatal and no rescue is possible. These are not conditions that training fully addresses. They are conditions that would test the resilience of any human being across years and decades, and the research base for understanding how people respond to such conditions over those timescales simply does not exist. We have never done anything like this, and we cannot fully predict what it would do to the people who attempted it. There is a concept sometimes proposed as a solution to the time and biology problems together, and that is some form of suspended animation or induced hibernation. If the crew could be placed in a state of dramatically reduced metabolic activity for the duration of the cruise phase of the journey, the problems of nutrition, psychological strain, and physiological degradation would be substantially reduced. The idea has genuine scientific basis. Certain animals undergo hibernation states that share some features with what would be needed, and research into therapeutic hypothermia and related techniques has produced insights relevant to the concept. But human hibernation of the kind required for an interstellar voyage, lasting years or decades, with reliable revival at the end, is not a technology that exists or that has a clear development path. The biological mechanisms that allow some mammals to hibernate safely are not simply transferable to humans, and the risks of extended metabolic suppression, particularly to the brain, are not well understood at timescales beyond ours. What the time and biology problem ultimately reveals is that the human body is a product of Earth, tuned over millions of years to a very specific set of conditions. Removing it from those conditions for extended periods causes measurable cumulative harm. The longer the removal, the greater the harm, and the less certain the outcome. An interstellar journey lasting decades would push the human body into territory where the medical literature offers no guidance, where the engineering solutions are untested, and where the margin for error is defined by the vacuum of space and the distance from any help. The stars are not simply far away in space. For human beings, they are far away in time, in biology, and in the fragile architecture of a body that was never built for the crossing. Chapter 5. Radiation and Survival. Of all the physical barriers to interstellar travel, radiation may be the most quietly relentless. It does not announce itself. It has no color or sound. It passes through walls, through suits, through the hull of a spacecraft, and through the soft tissue of the human body without any sensation at all. And it accumulates. Every hour spent in deep space, beyond the protective embrace of Earth's magnetic field and atmosphere, adds to a cumulative dose that the body cannot fully repair, and that increases incrementally and irreversibly the probability of serious harm. On Earth, we are shielded from the worst of the universe's radiation by two overlapping systems of protection. The first is the planet's magnetic field, a vast invisible structure generated by the movement of molten iron in the Earth's outer core, which deflects the stream of charged particles that flows constantly outward from the sun. The second is the atmosphere, a column of air roughly 100 kilometers deep that absorbs and scatters high-energy photons and particles before they reach the surface. Together, these two systems reduce the radiation environment at the Earth's surface to levels that biological life has adapted to over billions of years. Remove them, and the radiation environment changes dramatically. In low Earth orbit, astronauts receive radiation doses roughly equivalent to several times the annual dose experienced at sea level, partly because they are above most of the atmosphere and inside, rather than shielded by the Van Allen belts that trap certain categories of charged particles. On a mission beyond low Earth orbit, such as a journey to the Moon or Mars, the radiation environment becomes more severe still. The Apollo astronauts, who passed through the Van Allen belts on their way to the Moon, received doses that were carefully monitored and were considered acceptable for the short duration of those missions. A Mars mission, lasting perhaps 2 to 3 years in total, would expose a crew to radiation doses that approach or exceed the lifetime limits currently recommended for professional astronauts. An interstellar mission lasting decades would expose the crew to radiation doses that exceed those limits by a very large margin. The sources of that radiation are multiple and not all equally manageable. Galactic cosmic rays are the most persistent concern. These are high-energy particles, primarily protons and heavier atomic nuclei, that originate outside the solar system, accelerated to near-light speeds by the remnants of supernova explosions and other energetic processes in the galaxy. They arrive from all directions continuously at energies so high that no practical thickness of conventional shielding material can stop them entirely. The most energetic cosmic ray particles are extraordinarily penetrating. Adding more mass to a spacecraft's walls to stop them is a strategy with diminishing returns, because the interaction of the particles with the shielding material itself produces secondary radiation, a cascade of lower energy particles generated by the collision, that can, in some configurations, deliver a higher dose to the crew than the original particle would have done unimpeded. The Sun contributes its own radiation hazard in the form of solar energetic particle events, intense bursts of radiation associated with solar flares and coronal mass ejections. Within the solar system, these events can deliver dangerous doses in a matter of hours, and spacecraft designed for long-duration missions typically incorporate a small, heavily shielded storm shelter where the crew can retreat during the most intense episodes. Beyond the solar system, the sun's influence diminishes and solar particle events become less relevant. But galactic cosmic rays, which the sun's magnetic field partially suppresses within the heliosphere, become more intense in interstellar space. A spacecraft that has left the solar system behind is no longer partially shielded by the sun's own magnetic environment, and the galactic cosmic ray flux it encounters is the full, unattenuated background of the galaxy. The biological effects of high-energy radiation are well established in broad outline, though the details of long-duration, low-dose rate exposure remain an active area of research. Ionizing radiation damages DNA, either directly by breaking chemical bonds in the molecule, or indirectly by creating reactive molecules in the surrounding water that then attack the DNA. Cells have repair mechanisms for this kind of damage, and at low doses, those mechanisms are generally effective. But they are not perfect. Some damage is misrepaired, leading to mutations. Some damage is not repaired at all, leading to cell death. Over time, accumulated mutations increase the risk of cancer. Radiation exposure also affects the central nervous system in ways that are less well understood, with some research suggesting that high-energy heavy nuclei, a component of galactic cosmic rays, can cause neurological changes that affect cognition, memory, and behavior. Studies in animal models have shown cognitive impairment following exposure to simulated cosmic ray radiation, and while the translation of these results to humans is uncertain, the findings are not reassuring. Shielding remains the most straightforward approach to the radiation problem, but as noted above, it is an approach with serious limitations against the most energetic particles. Materials with high hydrogen content, water, polyethylene, and certain plastics are more effective at absorbing and scattering cosmic ray particles than metals like aluminium, because hydrogen nuclei are similar in mass to the incoming protons and can absorb their energy more efficiently in a collision. A spacecraft whose walls incorporated thick layers of water or hydrogen-rich plastic would provide meaningfully better radiation protection than one with thin aluminium walls. But the mass required for effective shielding against galactic cosmic rays is large, and every kilogram of shielding added to the spacecraft is a kilogram that must be accelerated to interstellar velocities, with all the fuel and energy consequences that entails. Magnetic shielding offers a different approach. If a spacecraft could generate a strong magnetic field around itself, analogous to the Earth's magnetosphere on a smaller scale, that field might deflect incoming charged particles before they reach the hull. This concept has been studied seriously, and small-scale experiments have been conducted to assess its feasibility. The results suggest that a superconducting magnet system could provide meaningful protection against lower-energy cosmic ray particles and solar energetic particles. But the most energetic galactic cosmic rays carry so much momentum that deflecting them would require magnetic fields of extraordinary strength, far beyond what current or near-future superconducting technology could produce at any reasonable mass. A magnetic shield effective against the full spectrum of cosmic ray energies would need to be extremely large or extremely powerful, and the engineering challenges of maintaining such a system reliably over decades in deep space are formidable. There is also the question of what happens when the spacecraft is moving at a significant fraction of the speed of light. At those velocities, the interstellar medium itself becomes a radiation hazard. The sparse hydrogen atoms that drift between the stars, harmless at low speeds, become high-energy particles in the reference frame of a fast-moving spacecraft. At 20% of light speed, each hydrogen atom encountered by the spacecraft carries the energy of a moderately energetic cosmic ray particle. At 50%, the energy is considerably higher. The flux of these impacts increases with speed, and at the velocities needed for a fast interstellar crossing, the interstellar medium transforms from an empty vacuum into something more like a continuous radiation environment. The spacecraft's forward surface would need to withstand not just occasional energetic impacts, but a sustained bombardment, and the secondary radiation produced by these impacts would add to the crew's cumulative dose. The radiation problem, like the fuel problem, does not have a clean solution within the bounds of current or near-future technology. It can be partially managed through a combination of shielding, magnetic deflection, careful mission planning to minimize exposure time, and medical countermeasures that reduce the biological impact of radiation damage. Research into radioprotective drugs and into biological interventions that enhance DNA repair is ongoing, and there is genuine hope that the pharmacological tools available to future space travelers will be meaningfully better than those available today. But even with improved medical countermeasures, the cumulative radiation dose from a multi-decade interstellar voyage would likely exceed any threshold that current understanding considers safe by a considerable margin. This is one of the barriers to interstellar travel that is most resistant to engineering solutions, because it arises not from a gap in our technology, but from the fundamental nature of the galaxy we live in. The universe is filled with energetic particles produced by violent astrophysical processes, supernovae, neutron stars, active galactic nuclei, and those particles travel freely through interstellar space, encountering whatever lies in their path. A spacecraft and its crew are not special in the eyes of a galactic cosmic ray. They are simply matter, and matter is what high-energy particles pass through. The stars shine across distances that take light years to cross. In the space between them, the galaxy's own energy fills the silence, particle by particle, in a radiation field that no hull has yet learned how to fully refuse. Chapter 6. The Speed Limit. There is a number at the center of modern physics that functions less like a measurement and more like a boundary. It is 299,792 kilometers per second. It is the speed of light in a vacuum, and it is, as far as current understanding extends, the absolute maximum velocity at which anything in the universe can travel. Not the fastest we have managed, not the fastest we expect to achieve with better technology, the fastest that physics permits for any object with mass, under any circumstances, using any method. The reason for this limit is not arbitrary. It emerges from the geometry of space-time itself, as described by Albert Einstein's special theory of relativity, published in 1905. The theory rests on two postulates. The first is that the laws of physics are the same for all observers moving at constant velocity relative to one another. The second is that the speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. From these two simple statements, a set of consequences follows that reshape the intuitive picture of space and time completely. One of those consequences is that as an object with mass accelerates toward the speed of light, the energy required to accelerate it further increases without limit. At low velocities, the relationship between force, mass, and acceleration behaves in the familiar Newtonian way. But as velocity increases toward the speed of light, the object's resistance to further acceleration grows in a way that no finite amount of energy can overcome. An object with mass can approach the speed of light asymptotically, getting ever closer without ever arriving. To actually reach light speed would require infinite energy, This is not a limitation of our engines. It is a limitation written into the structure of space-time. This has a direct and uncomfortable implication for interstellar travel. Even if the energy and fuel problems were somehow resolved, a spacecraft carrying mass, including a crew, could never reach the speed of light. It could approach it. At 90% of light speed, the journey to Proxima Centauri would take about 4.7 years. At 99%, about 4.2 years. At 99.9%, just over 4 years. The destination gets no closer as the speed increases. Only the time required shrinks, and the energy required to achieve each incremental increase in speed grows enormously. The last few percent of light speed costs more energy than all the preceding acceleration combined, and the final fraction of a percent costs more than everything before it. Relativity introduces another consequence that is both remarkable and deeply strange for any crew making such a journey. Time itself passes differently for an object moving at high velocity relative to a stationary observer. This effect, known as time dilation, means that a crew traveling at a significant fraction of light speed would experience less time passing than observers on Earth. At 90% of light speed, the crew would experience time passing at roughly 44% of the rate experienced by people on Earth. A journey that takes 10 years in Earth's reference frame would feel like about 4.5 years to the crew. At 99% of light speed, the crew's time passes at about 14% of Earth's rate. At 99.9%, at about 4.5%. In principle, time dilation could be used to make extremely long journeys subjectively manageable for the crew. At velocities very close to light speed, a crew could in theory cross vast distances within a single human lifetime as experienced aboard the ship, even though thousands or millions of years would pass on Earth during the same journey. This is not science fiction. It is a mathematically precise prediction of special relativity, confirmed by experiment in multiple forms. But it does not make interstellar travel easier in any practical sense. The energy required to reach those extreme velocities remains insurmountable with any known or foreseeable technology, and the civilization the crew left behind would be unrecognizably changed or simply gone by the time any return was possible. Time dilation also creates a communication problem of its own. A crew traveling at relativistic speeds would experience time passing at a different rate from mission controllers on Earth. Coordinating a mission, relaying instructions, receiving updated scientific data. All of this becomes complicated when the crew's clock and Earth's clock are running at different rates, separated by the compounding effects of both velocity and distance. Real-time communication, already impossible due to the finite speed of light, becomes even more conceptually complex when the two ends of the conversation are moving through time at different rates. There is one further consequence of approaching light speed that deserves attention, and it connects back to the radiation problem discussed in the previous chapter. As a spacecraft's velocity increases, the frequency of electromagnetic radiation it encounters in the forward direction increases due to the Doppler effect. At modest fractions of light speed, this shifts visible starlight toward the blue end of the spectrum. A beautiful effect, in principle. But at velocities approaching light speed, the forward-facing radiation environment becomes genuinely dangerous. Cosmic microwave background radiation, the faint afterglow of the early universe that fills all of space, would be blue-shifted into increasingly energetic X-rays and gamma rays. The sparse hydrogen atoms of the interstellar medium, as noted previously, would behave as high-energy projectiles. The faster the spacecraft travels, the more hostile the forward radiation environment becomes, imposing practical limits on achievable velocity that exist independently of the propulsion problem. The speed limit that special relativity imposes is not a frustrating technicality. It is one of the deepest features of the universe. It reflects the fact that space and time are not separate, independent backdrops against which events occur. They are a unified structure, and the geometry of that structure places firm constraints on how quickly any physical object can move through it. The stars are separated by distances that light takes years to cross, and nothing with mass can match light's pace. That asymmetry between the scale of the universe and the speed limit built into its foundations is perhaps the most fundamental reason why interstellar travel sits at the outermost edge of what physics can even consider permitting. Chapter 7. Shortcuts and their limits. Given the scale of the barriers described so far, it is natural that physicists and engineers have spent considerable effort looking for ways around them, rather than through them. If the direct route to the stars is blocked by energy requirements, fuel masses, biological limits, radiation, and the speed of light itself, perhaps there are other routes, geometrical shortcuts through the fabric of space-time that could reduce the effective distance, or theoretical mechanisms that could move a spacecraft without accelerating it in the conventional sense. These ideas are not purely fictional. Some of them emerge from legitimate solutions to Einstein's equations of general relativity, but each one, examined carefully, runs into its own set of physical barriers that are no less formidable than the ones they were designed to circumvent. The most widely discussed shortcut is the wormhole. In formal physics, a wormhole is a hypothetical topological feature of spacetime, a tunnel connecting two distant regions that would otherwise be separated by an enormous distance. The concept has a precise mathematical basis. General relativity permits solutions to its field equations that describe such structures, and the possibility was explored seriously by physicists including Albert Einstein and Nathan Rosen in 1935, which is why wormholes are sometimes called Einstein-Rosen bridges. If a stable wormhole could exist, a spacecraft entering one mouth might emerge from the other mouth in a completely different region of space, having traversed the tunnel, rather than the full distance between the 2 points. In principle, a wormhole could connect our solar system to a star 4 light-years away through a tunnel only meters long. The problems with wormholes are significant and begin with the question of whether they can exist at all in a form useful for travel. The Einstein-Rosen bridge described in the original 1935 paper is not traversable. It connects two regions of spacetime, but it collapses so quickly that nothing, not even light, can pass through it before it pinches off. To hold a wormhole open long enough for a spacecraft to transit, the throat of the wormhole would need to be threaded with a form of matter or energy with negative energy density, a property that ordinary matter does not possess. This hypothetical substance is referred to as exotic matter, and while quantum mechanics permits certain configurations of fields to have negative energy density under specific conditions, producing exotic matter in the quantities that would be needed to stabilize a macroscopic wormhole is not something current physics can describe, let alone achieve. The gap between the mathematical existence of a solution to general relativity's equations and the physical existence of a stable, traversable wormhole is enormous, and there is no established reason to believe that gap can be bridged. Even setting aside the question of stabilization, wormholes raise a further problem. They would need to be created or located. No wormhole has ever been observed. There is no evidence that they exist in any form in the observable universe. Creating one from scratch would require energy densities and space-time curvatures far beyond anything in the known universe, and threading it with exotic matter to keep it open would compound an already impossible engineering challenge. The wormhole is a mathematically permissible idea that exists at an enormous distance from physical reality. The warp drive concept, most formally described by physicist Miguel Alcubierre in 1994, takes a different approach. Rather than tunneling through space, the Alcubierre drive proposes contracting space in front of a spacecraft and expanding it behind, carrying the spacecraft forward in a bubble of flat space-time without the spacecraft itself accelerating in the conventional sense, because the spacecraft is not moving through space, but is instead being carried by the movement of space itself. The light speed limit, which applies to motion through space, would not technically be violated. In principle, the warp bubble could move at any speed, including faster than light. The Alcubierre drive is a genuine solution to Einstein's field equations, and its publication prompted serious scientific discussion. But the physical requirements it demands are extraordinary. Like the traversable wormhole, the Alcubierre drive requires exotic matter with negative energy density in quantities that various analyses have estimated at masses comparable to the mass of a planet, or in some formulations, the mass of Jupiter. Later refinements of the concept reduced the exotic matter requirements somewhat, but they remain far beyond anything physically accessible. Additionally, a spacecraft inside an Alcubierre bubble would be causally disconnected from the space in front of it, meaning the crew could not steer or control the bubble from inside. The bubble would need to be configured from outside before departure, removing any possibility of in-flight navigation. And the bubble's leading edge would accumulate particles from the interstellar medium, which would be released in a burst of high-energy radiation upon arrival, potentially devastating anything at the destination. Generation ships represent a very different kind of shortcut, not a geometrical one, but a biological one. If a single crew cannot survive the journey, perhaps the solution is to send a community large enough and structured enough to sustain itself across multiple generations, with the destination reached not by the original travelers, but by their descendants. The idea removes the biological time constraint by simply extending the time frame across generations, rather than trying to compress it through velocity or suspended animation. A generation ship traveling at a fraction of a percent of light speed could, in principle, reach nearby stars over centuries, with successive generations born, living, and dying aboard the vessel. The generation ship concept is one of the more sobering ideas in interstellar travel, because it trades physical impossibility for a different kind of difficulty: the social and ethical complexity of committing unborn generations to a journey they never chose, in an enclosed environment from which there is no exit. The population required to maintain genetic diversity over centuries has been estimated at several hundred individuals at minimum, and possibly several thousand. Governing such a community over generations, maintaining the technical knowledge needed to operate the spacecraft, preventing social fragmentation or conflict in a closed environment with no possibility of outside intervention. These are challenges that have no historical precedent and no tested solution. What the landscape of proposed shortcuts reveals is a consistent pattern. Each idea that attempts to work around the barriers of interstellar travel either requires physics that does not exist in accessible form, demands engineering on a scale that no foreseeable civilization could achieve, or solves one problem while creating several others equally intractable. The universe does not appear to offer easy passages between the stars. The shortcuts written into the mathematics of general relativity come with price tags in exotic matter, negative energy, and causality violations that place them beyond any practical consideration. The biological shortcuts involve ethical and social dimensions that physics cannot resolve. The barriers to interstellar travel are not a list of separate problems waiting for separate solutions. They are expressions of the same underlying reality, that the universe is vast, that its rules are consistent, and that those rules do not bend in favor of ambition. Chapter 8. What we have sent. Against the backdrop of everything discussed so far, it is worth pausing to consider what humanity has actually managed to send beyond the boundaries of the solar system. Not what we have imagined, not what we have calculated, but what we have done. The answer is both genuinely remarkable and quietly humbling, because the gap between what we have achieved and what interstellar travel would actually require is so large that it reframes the entire history of space exploration in a single comparison. 5 spacecraft have achieved or are on trajectories to achieve escape velocity from the solar system. The 2 Voyager probes, launched in 1977, are the most distant human-made objects ever built. Voyager 1 crossed into interstellar space, beyond the heliopause, where the sun's influence gives way to the interstellar medium. In 2012, becoming the first human-made object to enter that environment. Voyager 2 followed in 2018. Pioneer 10 and Pioneer 11, launched in 1972 and 1973 respectively, are also on outbound trajectories, though their transmitters have long since fallen silent. New Horizons, launched in 2006, is the most recently dispatched of the 5 and will eventually join them in interstellar space. Voyager 1 is currently traveling at approximately 61,000 kilometers per hour. At that speed, it would take approximately 73,000 years to reach Proxima Centauri if it were headed in that direction, which it is not. It is not headed toward any particular star. It is simply moving outward in the direction imparted by its original trajectory into the dark, the signal it sends back to Earth, generated by a transmitter producing roughly 22 watts of power, less than a standard household light bulb, takes more than 22 hours to reach us, traveling at the speed of light across the distance Voyager 1 has covered in nearly 5 decades of flight. That distance, impressive as it is in human terms, is a vanishingly small fraction of a light year. Proxima Centauri is 4.2 light-years away. Voyager 1, after nearly 50 years of travel, has covered approximately 0.002 light-years. It has barely left the neighborhood. The interstellar medium it now moves through is the same interstellar medium that fills the space between every star in the galaxy, and it will move through that medium for tens of thousands of years before approaching any other star system, long after every component has failed and every signal has ceased. What the Voyager probes represent is the current outer edge of human reach, not in terms of ambition or imagination, but in terms of physical hardware that humanity has actually placed in space. They are extraordinary achievements. They were designed in an era before personal computers, built with technology that would seem primitive by current standards, and they have operated continuously for nearly half a century, returning scientific data from the outermost reaches of the solar system and beyond. The fact that we can still communicate with an object that humanity launched in 1977, now billions of kilometers away, is a genuine testament to the skill and care of the people who built and operated them. But they are not interstellar missions. They are solar system missions that happen to be leaving the solar system very slowly. The difference between what they represent and what a true interstellar mission would require is not a difference of degree. It is a difference of kind. a spacecraft capable of reaching Proxima Centauri in a human lifetime would need to travel approximately 3,000 times faster than Voyager 1. The energy required to accelerate even a small probe to that speed dwarfs anything that has ever been produced for a space mission by many orders of magnitude. The Breakthrough Starshot initiative, announced in 2016, proposed a serious scientific attempt to close that gap, at least partially, and at very small scale. The concept involves using a powerful array of ground-based lasers to accelerate gram-scale spacecraft. Tiny chips carrying a camera, communication laser, and minimal instrumentation to approximately 20% of light speed. At that velocity, the journey to Alpha Centauri would take roughly 20 years. The scientific return would be limited but real. Even a brief flyby, transmitting images and basic measurements across 4 light years, would represent an enormous leap beyond anything previously achieved. Breakthrough Starshot remains a concept under development. The engineering challenges are substantial. The laser array required would need to produce power levels far beyond any existing facility. The tiny spacecraft would need to survive the acceleration phase, during which they would experience forces of tens of thousands of G for a matter of minutes. The communication link from 4 light years, using a laser aboard a gram-scale chip, would be extraordinarily faint, and there is no mechanism for deceleration. The probes would pass through the Alpha Centauri system at 20% of light speed, with no ability to slow down, orbit, or linger. What we have sent, then, is 5 slowly outbound probes from the 1970s and a concept for gram-scale flybys that has not yet been built. This is not a criticism. It is a measurement. It tells us where the frontier actually sits and how far that frontier is from the popular image of humanity as a species on the verge of reaching the stars. We are not on the verge. We are at the very beginning of a journey whose next meaningful steps have not yet been taken, and whose ultimate destination remains separated from us by barriers that this entire discussion has only begun to describe. Chapter 9. The Scale of Silence. There is a question that sits quietly beneath everything discussed in this documentary, and it deserves to be looked at directly. If interstellar travel is this difficult, if the barriers are this fundamental, this deeply embedded in the laws of physics, then what does that mean for the universe as a whole? Not just for humanity, but for any civilization that has ever existed anywhere in the galaxy, looked outward, and asked the same questions we are asking tonight. The Milky Way is estimated to contain somewhere between 200 billion and 400 billion stars. It is approximately 13 billion years old. Around many of those stars orbit planets, and the discovery of exoplanets over the past 3 decades has confirmed that planetary systems are not rare exceptions, but common features of stellar formation. The conditions that gave rise to life on Earth, liquid water, stable energy from a nearby star, a reasonably sheltered chemical environment, may not be unique. Some fraction of the galaxy's planets may have developed life. Some fraction of those may have developed intelligence. Some fraction of those may have developed technology. Given the age and scale of the galaxy, even a small fraction of stars hosting technological civilizations would produce numbers large enough to fill the imagination. And yet, in all the decades of listening, scanning, and searching, no confirmed signal from another technological civilization has ever been detected. No spacecraft of non-human origin has ever been identified. No unambiguous evidence of engineering at astronomical scales has been observed. The galaxy appears, from our vantage point, to be silent. This silence has a name. It is called the Fermi paradox, after the physicist Enrico Fermi, who reportedly raised the question during a lunch conversation in 1950. The paradox is not really a paradox in the logical sense. It is a tension between two observations: the apparent likelihood of other civilizations existing somewhere in the galaxy, and the complete absence of any evidence that they do. Many explanations have been proposed, ranging from the possibility that life is far rarer than optimistic estimates suggest, to the possibility that intelligent civilizations tend to destroy themselves before reaching the stage of interstellar communication, to the possibility that other civilizations exist but have chosen not to make themselves known. One explanation that is sometimes overlooked in popular discussions is simply this: interstellar travel is as hard for everyone as it is for us. The barriers described in this documentary are not barriers that arise from human limitations or from the specific circumstances of Earth. They arise from the laws of physics, which are the same everywhere in the universe. Any civilization, anywhere in the galaxy, faces the same energy requirements, the same fuel problem, the same speed limit, the same radiation environment, the same biological constraints. The universe does not offer shortcuts to anyone. The silence of the galaxy may reflect not the absence of other minds, but the presence of the same walls that stand between us and the stars. This is a thought worth sitting with. The interstellar medium that Voyager 1 now moves through is the same medium that separates every star from every other star in the galaxy. It is crossed by light and by cosmic rays, and by the occasional probe moving at speeds that make the crossing take tens of thousands of years. It is not crossed by anything we have ever built at speeds that would make it navigable on human timescales. And if the physics that governs our situation governs all situations equally, then the galaxy may be full of civilizations that have looked outward with the same longing we feel, calculated the same numbers we have calculated, and arrived at the same conclusions. The scale of silence is not emptiness. It is distance, expressed in the only units the universe offers. Light years of vacuum, filled with radiation and thin gas, and the occasional dust grain, separating islands of warmth and light that are simply too far apart for anything that obeys the known laws of physics to bridge in any practical sense. The stars are not hiding from us. They are just very, very far away, in a universe that moves at a speed limit of 300,000 kilometers per second and offers no exceptions. There is something clarifying about this perspective. The silence of the galaxy, viewed through the lens of everything we have explored tonight, begins to look less like an absence and more like a reflection of the universe's own geometry, its own rules, its own deep indifference to the wishes of any particular species that happens to have developed the ability to ask questions about its place in the cosmos. We are not alone in facing these barriers. We are simply one of the places in the universe where the barriers have been clearly seen and honestly described. The nearest star is 4 light years away. The physics that separates us from it is the same physics that holds atoms together, that keeps planets in orbit, that causes stars to shine. It is not an obstacle in the way that a wall or an ocean is an obstacle, something that exists independently of the traveler and might be overcome with sufficient ingenuity. It is the structure of reality itself, and it applies with perfect consistency to everything in it. That is the scale of the silence, not hostile, not personal, not final in any dramatic sense, just vast and patient, and entirely indifferent to how far we have come or how much further we would like to go. Chapter 10. A Quiet Place in the Dark. We have covered a great deal of ground tonight. We began with a single number, 4.2 light years, and followed it through energy and fuel and biology and radiation and the geometry of space-time itself, through the silence of the galaxy and the humbling smallness of everything we have so far managed to send beyond our own solar system. And now we arrive at the end of that journey, not at a destination, but at a quiet place to rest with what we have found. The picture that emerges from an honest examination of interstellar travel is not a comfortable one for anyone who has grown up with the idea that the stars are waiting for us. They are not waiting. They are simply there, at distances that the laws of physics make extraordinarily difficult to cross, separated from us by a vacuum filled with radiation and governed by a speed limit that no amount of engineering has yet found a way around. The barriers are real, they are deep, and they are consistent. They do not weaken with time or yield to optimism. And yet, there is something in that picture that is not discouraging, if it is looked at from a slightly different angle. The same physics that makes the stars so difficult to reach is the physics that makes them shine. The nuclear processes that power stars across the galaxy are the same processes that, if harnessed for propulsion, represent our best theoretical hope of crossing interstellar distances. The space-time geometry that imposes the speed limit also produces time dilation, which opens the strange possibility that a traveler moving fast enough could cross vast distances within a single subjective lifetime, even if the universe ages around them. The universe that makes interstellar travel so hard is also the universe that produced planets and oceans and the long chain of chemistry and biology that eventually produced creatures capable of asking why the stars are so far away. There is also something worth considering in the fact that we understand these barriers as well as we do. A century ago, the concept of the light speed limit was newly established. The rocket equation was barely a decade old, and the existence of other galaxies beyond the Milky Way had not yet been confirmed. The framework within which we now understand the challenges of interstellar travel is itself a remarkable achievement, built from centuries of observation, mathematics, and careful experiment. We know why the stars are hard to reach, not because we have failed to reach them, but because we have understood the universe well enough to calculate what reaching them would require. That understanding has value independent of whether the journey is ever made. The physics of high-velocity travel, the biology of long-duration spaceflight, the engineering of closed life support systems, the mathematics of energy and propulsion. All of these fields have produced and will continue to produce knowledge and technology that improves life on Earth and expands the reach of robotic exploration throughout the solar system. The pursuit of the impossible, or the nearly impossible, has a long history of yielding the merely difficult along the way. It is also worth remembering that the timescales involved in the universe are not the timescales of a human lifetime, or a century, or even a civilization. The Sun has approximately 5 billion years of hydrogen fuel remaining. The red dwarf stars scattered throughout the galaxy will burn for trillions of years. The universe itself, if current understanding is correct, will continue to expand and cool for timescales so vast they have no meaningful human equivalent. Against that backdrop, the fact that humanity in its current form, with its current technology, cannot cross interstellar distances is not a permanent statement about what is possible. It is a statement about where we are right now, in the very earliest moments of a technological civilization on a small planet orbiting an unremarkable star. Whether future generations, centuries, or millennia from now will find solutions to the barriers described in this documentary is a question that cannot be answered tonight. Perhaps the physics will yield something currently unseen. some property of space-time or energy that opens a door we have not yet found. Perhaps the barriers will stand forever, and humanity will remain a civilization of one solar system, looking outward at a galaxy it can observe but never enter. Perhaps something in between. Robotic probes reaching nearby stars over centuries, tiny ambassadors of a species that could not follow them in person. None of these outcomes diminishes the value of understanding where we stand. The stars that fill the night sky are real places. They have histories measured in billions of years. Many of them are orbited by worlds, some of which may be warm and wet and chemically complex in ways that matter enormously. The light that reaches our eyes from those stars left its source years, decades, centuries, or millennia ago, and it carries within it information about the physical processes occurring at distances our fastest spacecraft could not cover in 1,000 human lifetimes. We live in the middle of something vast and old and largely unreachable. The universe does not owe us passage through it. It simply is what it is, enormous, ancient, governed by rules that apply equally everywhere, indifferent to our wishes but available to our understanding. That understanding is not nothing. It is, in its quiet way, one of the most remarkable things that has ever happened in this corner of the galaxy. A species that evolved on a single planet, that has existed in its current form for only a few 100,000 years, has worked out the geometry of space-time, the energy of stars, the structure of matter, and the precise reasons why the nearest star is so very difficult to reach. The stars are far away, the physics is clear, and on a calm night, with enough time to think carefully about both, there is something deeply restful in simply knowing that. If this was a good companion tonight, a like or a subscribe helps other curious minds find their way here.